Okay, we will go through some important points in the class 12 physics chapter 6 electromagnetic induction. Okay, so what is electromagnetic induction? The phenomenon in which electric current is generated by varying the magnetic field is appropriately called electromagnetic induction. That is, we are generating electric current by varying the magnetic field. This is the Faraday's experiment. Here show that it is a relative motion between the magnet. This is a magnet and the coil that is responsible for the generation of the electric current in the coil. Okay, when you move the magnet, this flux changes and there is a current induced in this coil, and you can see that in the galvanometer. When a bar magnet is pushed towards the coil, the pointer in the galvanometer deflects. That means there is a current through this coil. So in the second experiment, instead of magnet, they are using a coil. Okay. The direction of the current in the coil. So we can use the galvanometer or you can use bulb also. Okay, if you use a more powerful battery here, then the more flux will be there, then the more flux change and then the more current. So you can also use a iron core inside this coil to increase the flux, magnetic flux. So you can also, if you move this coil very fast, then flux changes also will be very fast and more current will be induced. When CO2 is moved away, the galvanometer shows the deflection again. This time is when this coil is moved in and moved out, in both sides the direction of the current is changes. So we are moving into the thing in current one direction, moving away from current one direction. So in this experiment they are using a switch, on-off switch. It is observed that galvanometer shows a momentary deflection when tapping the key is pressed. Okay, the pointer in the galvanometer returns to zero immediately. That moment there will be a flux change. When you close it, that moment there will be a flux change. After that there is no flux change. So that deflection will again come to the normal. Okay, closing and opening, momentarily there will be a flux change. After that it will be constant. When the key is released also, the momentarily there will be a flux change and deflection again. This is the equation for the formula for the flux. This is the flux is directly proportional to the magnetic field area of cross section, this area, and the angle between this magnetic field and the area vector. See, this is area vector and the magnetic field angle between them is theta. Okay, so this will be maximum when theta is 0. Okay, when theta is 0, cos 0 is 1, then BA. That is the angle, the area vector and these are in parallel. That will be maximum flux. The magnetic field, suppose this is a uniform magnetic field. If the magnetic field has a different magnitude and directions at various parts of the surface, then this will be the flux. That is the summation of the all areas, flux in all areas. So the flux unit is Weber, this one. This is the Faraday's law of induction. The magnitude of the induced EMF in the circuit is equal to the time rate of change of magnetic flux through this circuit. So induced EMF is the rate of change of flux over the time. Okay, this negative sign indicates, this is important, the direction of the induced EMF and hence the direction of the current. Negative sign indicates okay, this EMF induced in such a way that it opposes the original magnetic field that caused this induced current. So if you have an n number of turns, then you have to multiply that flux with n. Okay, here for the one turn, this is for the multiple turns. So based on that, EMF can be increased by increasing the number of turns. This is directly proportional. So consider the experiment signal A. What you can do to obtain the large deflection in the galvanometer. As I said, if you use the soft iron core inside the coil C2, you can increase the flux. Then you can connect to a powerful battery or make the arrangement more rapid towards this coil. Okay. You can also use a bulb instead of the galvanometer. So here this is the flux change formula. So there is arrangement 45 degree between the magnetic field and the area vector. So this is this is the change in flux. This flux is from this. They are taking this. Note that the earth magnetic field also produces a flux through the loop. That is a steady field. Okay, it is not changing over the time. Okay, steady field which does not change within the time span of the experiment, and hence it does not include in any EMF. Okay, EMF induced only there is a change in flux over time. Okay, earth magnetic field does not change over the time. That is important. So here computing the EMF, we are using number of turns. Note that the magnitude of the X and L are estimated values. Their instantaneous values are different and depend upon the speed of the rotation of the particular instant. Lenz's law. The polarity of the induced EMF is such a way as tend to produce a current which opposes the change in magnetic flux. Okay, this is regarding Lenz's law. I have a diagram which shows various scenarios. Okay, you can go through this. How if you move the magnet in which direction the current will be induced, and which direction this opposing EMF will be produced. Okay, so here you see. So here there is no movement, no change in the induced flux. Okay, no current, no induced flux. Okay, here the magnet is north pole is moving towards the field. Okay, we are bringing the towards the field. Okay, so the induced flux increases in this case because we are moving towards induced flux increases. The current is in this direction. So the induced flux in the opposite direction to this. This is in the flux in this direction. The induced flux will be opposite direction. So that flux change, it resists the flux change. Okay, that is the Lenz's law. So in this case, you see this induced flux decreases because we are moving this direction. Okay, this now we are moving magnet moving up, so the induced flux decreases. Current in clockwise. Okay, here is the current in counterclockwise, current is clockwise, because here is coming down, magnet is coming down, is magnet moving away. The induced flux in this same direction as this. Okay, these both are in the same direction, so that it will offset this decreasing flux, so it will try to maintain, resist the change in the flux. Okay, so here again it is moving down, but this time is the south pole here. See here, this is not here south pole. The induced flux again increases because we are moving it down. So the current is clockwise, the flux direction is downwards. Here you see, this is the flux direction, so it is opposing the flux change. Okay, like that they are given the various scenarios in this, so you can go through, so you will understand the Lenz's law. See here, the current when magnet is moved to a current in this direction, it is going away current in the opposite direction. Okay, so here this circle is moving in towards the field, and this is moving away from the field, this is also away from the field. Okay, the important thing is that when this is outside the field, then there won't be any flux change. Okay, so no EMF will be induced when they are outside the field. They are completely inside the field also, no EMF will induce, because the flux will be constant within this area. When you are completely inside the field, no flux change, and when completely outside the field also, no flux change. Okay, so when you are coming closer to the field, the flux loop ABCD increases. The induced current must flow along the path, okay, so that it opposes the increasing flux. When you are coming towards the field, the flux will increase, so the induced current should oppose it. But here this is going away, flux will decrease, the induced current will oppose this change. Okay, so like that the direction will be. Note that this is very important. There are no induced current as long as the loops are completely inside or outside the region of the magnetic field. Completely inside, they are completely inside also, no current will be induced, because flux change won't be there. When they are completely outside also, no current will be induced. Okay, that is important here. Okay, see here this area changes. Rectangular and circular loop coming out of the magnetic field in the free region with the constant velocity. In which loop do you expect the induced EMF to be constant during the passage out of the field? Is not okay. Constant, it will be constant only this, because in this case the area is changing. See here, the induced EMF is expected to be constant in the case of the rectangular loop. In case of a circular, the rate of change of the area of the loop during the passing out of the field N is not constant. So hence induced will vary accordingly. Okay. Current can be induced on by changing the magnetic flux. Okay, see, only when changing the magnetic flux current can be increased, not electric flux. Okay, here they are saying whether a closed loop normal to the constant field between the plates of the capacitor, it is the electric field. Okay, changing the electric flux current cannot be induced, only magnetic flux, it change in magnetic flux induce the current. Okay, that is what they are mentioning now. Current induced, no current will be induced in either case. Okay, current cannot be induced by changing the electric flux. Electric flux change will not induce the current. Motional EMF, here these are the conducting wires, we are moving this. Okay, so now when we moving this conductor, the area changes. Okay, area changes. that is important here. Phi equal to okay B Lx B into area. So this is the emotional EMF. Dx by dt is velocity. Okay, rate of this x is changing over the time because this conductor is moving. So this x is changing. Dx by dt is velocity BLV. EMF BL is a motional EMF. There we are able to produce the induced EMF by moving the conductor. Okay, here we are not changing the magnetic field, but moving the conductor, the flux changes because the area changes. Okay, when you change the area, moving the conductor, the flux changes. So we are not changing the magnetic field. Here moving the conductor. So the EMF can also be expressed as the work done per unit charge. Okay. Stationary conductor, the force on the conductor. Okay, this is the formula. Lorentz force. When you rotate a rod, the free electrons move towards the outer surface. That is why EMF induced. When you rotate a rod along the ring like this, the free electrons move at the outer surface of the rod. That is why EMF. Thus, the resulting separation of charges produce the EMF. EMF in the rotating rod. Okay, this is the angular velocity, radius. Linear velocity equal to angular velocity in the radius. 2 pi into linear frequency. 2 pi into linear frequency is the angular frequency here. This equation is from this. Here we are made this equation here. Okay, of BW R square. So we have that equation here. The number of spokes is immaterial because the EMF across these peaks are parallel. When you have parallel voltage, the voltage will not add up. Okay, that is the here. So they are immaterial because the EMF across these spokes are parallel. In parallel means the voltage will be same. Okay, it will not increase the voltage. Here in this wheel, all these spokes are in parallel. Force on a conductor in a magnetic field. This is the formula. This is already seen in the other chapters. So when a change in charge flow is change in flux, okay, or the radius resistance. So here you see up to this point there is a magnetic field, but in this region there is no magnetic field. Okay, see up to this point the flux will increase, and after that in this region when we move there will be constant because there is no magnetic flux here. B from 0 to B. Okay, 0 to B only it will change, flux will change. After that it will be constant because only this flux will be there. Here there is no flux. So induced EMF also here 0 between B and 2B because there is no flux change here. That is why induced EMF will be 0 on that region, in that region movement. So they are given the graph. Here area increases, here area decreases. In this place area is constant. This is EMF. See here the flux in the positive direction, EMF in the negative. Here negative was because of that negative sign between the flux and EMF. So here because of this V square we get a positive only, okay, no negative because it is square. So you can try moving in the opposite direction, that is after you moved this place, then try moving this conductor up to this point and do the graph like this. Eddy currents. When bulk pieces of the conductor are subjected to the change in magnetic flux, induced currents produced in them. However, the patterns resemble the eddies in water. This effect was discovered. So this is eddy current. You see the direction of the current when it is coming to the magnetic field, moving away from the magnetic field. These are the copper plate, conducting plates. Okay, and coming close, what is the direction of current, and moving away, what is the direction of the current. This is the magnetic moment, current in the area. Eddy currents are undesirables. They heat up the core and dissipate electrical energy in terms of heat. So you can reduce the eddy current by doing this lot like this. Okay, this way you can reduce the eddy current in the plates. You can do like this. These are some of the applications of the eddy currents: magnetic braking system, electromagnetic damping, induction furnace, electric power meters. See, when you throw a magnet inside the pipe, what will happen in the aluminum pipe and what will happen in a conducting pipe? They are comparing because the difference. Electromagnetic, they may note that the eddy currents are not generated in the PVC pipe because they are not conductors. PVC pipe no eddy current. Okay, as the material is, there is no conductor, it's insulator, whereas aluminum is conductor. So aluminum conductor, eddy current is generated, but PVC pipe insulator, no eddy currents. Inductance, flux change. Okay, unit of induction Henry, H. Mutual inductance means inductance due to the one coil. Okay, current in one coil, inductance in other coil. Okay, M12 is called the mutual inductance of the solenoid with respect to the two. M12 means mutual inductance at one with respect to two. For this solenoid arrangement, they are deriving the equation, one solenoid inside the other. So this is mutual inductance of 2 with respect to 1. So here you see mutual inductance of 2 with respect to 1 and the current in 1 they are using. Okay, the number how they are used. Mutual inductance at 2 depends on the current in 1. Okay, that is what I mean. Similarly, mutual inductance at 1 depends on the current in the second coil. Mutual inductance will be same, M12 equal to M21 equal to M. Okay, both the coils. So here you have to be careful when you compute the flux. When you have the mutual inductance, which coil current, which coil flux we are using. Okay. Note that M12 from the above is 5-1. Assuming the magnetic field B2 is uniform over the The varying current in a coil can induce EMF in the neighboring coil. The magnitude of the induced EMF depends on the rate of change of current and mutual inductance. Okay, this is mutual inductance, the rate of change of the current. Self inductance. Okay, change of flux through the coil by means of varying current to the same coil. Same coil. Okay, that is self inductance. Is not, this inductance is not because of the other coil, it is because of the same coil by varying the current. So this is the mutual inductance or back EMF. This is also called back EMF. This is called constant L into di by dt. This L is a constant. The self-induced will always oppose any change and increase and decreasing of the current in the coil. So when you substitute N equal to NL, that is small n into L for by equal to BA, we will get this formula. The self-induced EMF is also called back EMF. Okay, this is also called back EMF. This is the magnetic potential energy stored in the coil. Okay, magnetic potential energy stored in the coil. This is self-inductance in current. Self-induction constant. See, whether it is electrical energy or magnetic flux, in both the cases, energy is proportional to the square of the field strength. Okay, we have already obtained the relation between electrostatic energy stored per unit volume in the parallel plate capacitor. Okay, that is electrostatic energy. This is magnetic potential energy. In both the cases proportional to the square of the field strength. Square of the field strength. So the square of the field strength. AC generator. The phenomenon of electromagnetic induction has been technologically exploited in many ways. An extremely important application is generation of the AC. So here rotation, how EMF changes by rotating this. AC generator converts mechanical energy into the electrical energy. So this is the instantaneous value of the EMF in the AC generator, NBA sin omega t. And this term is called this E naught sin omega t. So this is at various angle. What is the EMF we produce? At the angle between BA is 0 here, sin 0 is 0. Here angle between area vector and field vector is 90 degrees, sin 90 is maximum. Again 180 degree is 0. So like that cycle repeats at various angles of the angle between the magnetic field and area vector. This is how this AC generated. Hydroelectric generator. Suggests that your hypothesis of the doubtful validity. Certain kinds of fish are able to detect small potential differences. Okay, fish are able to detect small potential difference. However, in this fish, special cells has been identified which detect small voltage differences. Fish detect small voltage difference. In birds, no such cells has been identified. Thus, the migration pattern of the birds continues to remain a mystery. How birds migrate, is not known, is not clearly known. In summary, these are again the equations: flux, EMF, force, eddy current. Okay, this is back EMF or the self-induced EMF. Okay, these are the dimensions, so you can go through this.